Hi everybody, welcome back. In this lecture I'm going to talk about the interaction of charge and about methods of charging. So I think again all of you know about when two objects are the same charge, they will actually repel each other, as this image right here, and that unlikes attract. Well, funny story or good news, or I don't know how you want to take this, but there's actually different ways you can think about this, and this becomes really complicated really quickly. So I'm going to talk a little bit about more interactions that are involved with attraction or repulsion of charges. And then we're going to talk about actually charging things. In this, image that we have right here, they're already charged, but how do you get it to become charged? So we're going to talk all about that. And our big question is, how does charge interact with matter? So once again, if you have an object, how does it move? Or how do we move charges? All this fun stuff here. So this video is pretty hefty. There's a lot of information, so just brace yourself. In fact, I could have done this in 2 lectures, but I'm going to do it as one, which I usually do anyway, but just letting you know that this is a lot of information here. So the first part of the lecture, we'll talk about charge interactions. We'll talk about attraction, repulsion, and neutral. We'll talk about what that means, and this thing called polarization. And then we'll talk about how you charge objects, and it depends on if it's conductor or insulator. You might have heard those words before, so I'll reintroduce those words and talk about that. And then we'll talk all about neutralizing objects, which is just a really fancy word for grounding, and we'll talk more about these things. This whole section is much more conceptual. There's actually, I don't think there's any calculations in this section, so again, I don't know, for some of you that's good and for some of you that's bad, so just be aware that this is all conceptual physics. Just a review again, like charges repel and unlike charges attract, and you can see that image there. But another really interesting thing is that these charges are repelled by the same amount of force. So notice the arrows, the same length, right? But they're opposite, so that is a consequence of Newton's third law. And it's true for whether you attract or repel. So in other words, this right positive charge feels the same force as this left positive charge. They don't feel different forces. And that's true even if this one was a bigger charge, right? Just like with Newton's third law, if this was a bigger car and a smaller car and they collide, they feel the same force. It's the same thing here, and it just, your mind doesn't wrap around it quite easily because you assume a bigger object will push more. That's not the case. In this case, it's going to be pushing the same. We'll pause on calculating the amount of force until the next lecture, which is Coulomb's law, but for now I'm just going to mention it, that these get repelled by one another. So the question is, these are already charged objects, but can neutral objects attract and repel? Well, it turns out that they can attract. It's really sad that I literally have nothing to do these demonstrations with, so it's really sad. But I'll kind of draw it anyway. So what you can do is you could actually create an attraction with a neutral object. So what happens is that first of all, let me just clarify, 2 neutral objects cannot attract one another. So in order to get an attraction, you need one object that's already charged, and then you'll have a neutral object. And if you have a neutral and charged object, you'll cause an attraction. And it all has to do with this case called polarization. So polarization happens when you take a neutral object, and because of the presence of an outside charge, like this balloon here, we cause the charges to shift or separate. So notice that normally the charges would be on top of each other, but these electrons here on the balloon want to be pushed away from these electrons here. And because of that, it looks like this thing is positive on one side and negative on another side. But this is actually electrically neutral, even though it looks charged, because the number of charges, number of positive and negative charges are the same. So if I were to count them, I'm not going to, well, maybe I will. Hold on. Oh, my program's not up, I'm sorry. I thought sometimes I think I do these things and then I don't. And while I'm actually kind of disrupted here, I'm going to go ahead and get another program going while we're talking about this stuff. Okay. Here's exactly the same thing, but now with a nice demonstration for you. So notice that neutral object doesn't attract a neutral object. And notice that's true here. In fact, this program, if this was attracted, my hand is up here just to be dramatic, but notice the balloon's not moving, right? If I put the balloon here, it just stays here because I moved it. If I put it slightly right here, etc., it's not being attracted, as you can see right there. So yeah, let me go ahead and do that. So let me charge up this balloon. I'm going to take this sweater. I'm just going to rub off all the electrons so you get them all. And there we go. So if I let go of the balloon right now, I hope you'll notice, I'm actually holding it with my mouse. I know you can't see it, but my mouse hand. And then I let it go. And you can see it is attracted because we have opposites, right? But look at the wall. The wall has an equal number of positive and negative charges. So if I bring this close to the wall, watch what happens to the electrons. Oh, see how they get pushed away? Pretty interesting, right? Now, first of all, I hope you notice that the positive charges in both cases never move, right? They're fixed in the atom. They're not going to transfer ever. So notice that the wall charges don't move. But if I leave it right here, we could see that there's a slight positive charge toward the balloon and a slight negative charge away from the balloon. The negatives push away the negatives, the charges, the balloon is now attracted to that spot. See, if I let go of my mouse right there, it gets attracted. Now, the force is weak when it goes far away. So in other words, if I do this, this has way more charge, therefore more force. But if I bring it close enough, you can see the attraction there. To repeat, what this part of the wall is, right here, is called polarization. Now notice the bottom's not polarized, nor the top, because this charge are not separated. And this is still a neutral object. So coming back to my point here, a neutral object can be attracted to a charged object as long as it's charged. There's a great multiple choice question coming up on your next quiz. Is which one is the polarized object? It's the wall. It's the neutral object that gets polarized. Like that. And like I said, you can't have two neutral objects attract one another. There is no interaction of charge, no way to separate charge, so there will be none. If this were a classroom setting, I would take a rod. This is not a rod. I would charge it by rubbing it, and then I would take it and put it next to a can. This is my daughter's beautiful artwork. You can see her can. But if I put it next to the can, you'd see the can be attracted. So you're missing out on that nice demo. So here's a little check for you, another great example of a multiple choice question. You know, which one is the following pictures correct? So take a moment and see if you could do this. I'll pause for about 5 seconds so that you can think this through. Another good multiple choice question. Okay, I hope you looked at it and the answer is D. All the other ones don't make sense. So the first one, it doesn't actually polarize. So this one would be attracted. This one, this positive charge right here, does not attract extra positives. And putting it on the other side doesn't affect things. It's still attracted. It's not attracted to positives. You need to have the opposite. So negatives are attracted to the positives get pushed away. Now, note about this drawing. Just like I told you before, the positive charges do not move. But you could see that they're here, right, versus over there, and that they moved, right? Now, what we do is we model net charges, not the actual charges on the thing. So in other words, the protons are still in place, but we just like to draw positives here because this side is more positive, not because the protons have moved. So big distinction there. All right. Here's another great question. So your physics teacher has prepared the classroom and suspended several inflated balloons from the ceiling. Upon entering the room, you observe two balloons being drawn toward each other. The attraction of the balloons for one another provides evidence that both balloons are charged with the same type, with opposite type. Both balloons are charged with either type. Only one balloon charged, one is neutral. At least one of the balloons is charged and the other is charged or neutral. So once again, take a second to think about what would cause that interaction that you see there, and I'll pause for 3 seconds. Okay, I hope you chose the answer E in this question. At least one of them's charged, and this one can be charged or neutral, as long as it's charged with the opposite one of this right here. So the answer is E. Ooh, this one's fun. This is a thinking one. Like I said, this can escalate really quickly. So we know for a fact that B is negative. B is in fact negative. And the question is, what is A and C? Well, A and C are repelling each other, which means these have to be the same type of charge. And if that's true, then A has to be charged and has to be positive. And C has to be the same because it's repelling, so C is also positive, like that. So these can get tricky. You have a few in your homework, I believe, and you'll have a few on your exam. So be ready for the more interactive interaction of charges type question. Okay, so now we're going to shift gears and talk about how to charge objects. So once again, it's all about the removal of electrons. I can't stress this enough. Protons are not fixed. You'll see multiple choice with motion of particles of protons. Those are always wrong. Like literally, anytime you see protons moving, it's wrong. Because it's always the electrons that transfer. So if I took a cloth and I rubbed it, what happens is the silk cloth gains the electrons, leaving it positive charge. So even though it's positive, it's because we removed electrons, not so much that we put protons here. So notice that terminology. Something else I just want you to be familiar with, is what is called an electroscope. Again, this would be a real class demonstration I would show you, so you have to use your imagination. But it's actually a really, really like simple device, although it looks a lot more crazy. But what you do is you take an object and you put it near the charge sampler, and this thing will start to deflect when it's charged. Now, the reason why it starts to deflect is because the same type of charge gets distributed. So naturally, the negative here will be repelled by the negative here. And this thing is able to spin. So it will show things are charged. The higher the deflection, the more charge you see. So these are referred to in many cases, and you'll see this on your quiz as well in terms of, is this object charged or not, etc. These can also be polarized. So in other words, you can actually have, let me just make one more note about this. These can be polarized, so you could have a situation where you have your electroscope and you have the deflection, right? The needle like that. So what you could have or see, I don't know where I changed this. I have to figure this out. Is it here? Oh, it's right there. That's where it is. Woo! I figured it out. I want blue instead. So much better. I think green is usually not a great color either. Usually I need something more vibrant, maybe like bright green. There we go. Oh, I like these colors way better. Okay, anyway, the point is, electroscopes can be polarized. So in other words, if I held a negative rod above it, above and not, so if I had a rod that was negative, right? Sorry, I'm at the top here, which is really silly. If I had a negative rod, it's going to push away the electrons down here, which means the top of this would be positive. That's if the rod does not touch. That's important. If the rod doesn't touch, this will become polarized. In other words, it doesn't have the same charge like you see below. If the rod does touch, then you have something like this. For example, if I had a negative rod touching, the electrons want to get away from that negative rod. So the electrons move to that. And this has the same charge throughout its electroscope. So in other words, notice there's no positives here. No positives there. Same charge in electroscope. So that's a very important note about the electroscope, that it could have positive and negative charges on the same thing, but this is electrically neutral. Remember the term because it has the same amount of charges. So this is electrically neutral but polarized, and this is charged with a negative charge. Okay. In terms of generating charge in objects, it depends on the type of object, and in fact, it's actually material based. So you can get really, really crazy with electron configuration of chemicals and elements and atoms, and that's really where the basis is. But it's just easier just to kind of group things in a little more simpler terms. There is definitely exceptions to all the rules that I talk about, but like always, we're going to look at the simplest cases first. So I'm going to put everything into two bowls, conductors and insulators. Now, conductors are generally metals, and that's because in metals, electrons are able to move from atom to atom. And if you're all made out of metal, like the majority of this can, which is metal, I mean the outside's paper, but this would be a good conductor if you didn't consider the paper. I don't have any good conductors around me at the moment. The way I charge this is different than what I do with an insulator. So tap water is a conductor, mostly because there's other stuff in the water itself. So minerals are in the water. So there's, metals in our water. We drink it all the time. It's fine. But that's what's causing it to be conductive. They say to get out of the pool because of that, and that's true. And also humid weather is a good conductor. So in other words, during the summer, you might notice that you never get shocked as much as you do in the winter, right? So let me talk about that. So if you look in insulators, don't allow electrons to move easily. So we have to charge them a different way. We literally take the electrons off of a single spot. Insulators include plastic, styrofoam, gloves, glass. Pure water is actually an insulator. So if there's nothing else in the water, like distilled water, like the water you get from chemistry, then it in fact is is a insulator. There's some cool online videos to look at this if you're interested. If you just Google pure water conductivity, you'll find some fun videos. And then I said dry air. So what happens is in the winter time, if you take off like your wool sweater, you rub off the electrons, like literally. And what happens is that the air prevents the electrons from leaving you, so you remain charged. Whereas in humid weather, if you did that, if you took off a sweater, the charge will go into the air because there's some metals in the air. I mean, I'm not actually floating metal around, but the point is that air, the humidity, the water and being humid allows the electrons to have a place to go. It's kind of like a barrier. Dry air actually puts like a barrier around you, so you keep your charge, so it's more likely that you get shocked. This is also a demonstration I do in class, which is very sad that I can't be there. But this is an insulator, so I tried to do these here in my house, but I don't even have these. I don't have styrofoam cups, which is the ones that are the best for this demonstration. And then I use seltzer cans. I don't usually drink soda, but I drink a lot of seltzer. But it's really cool. I could do some of these demonstrations, so you have to use your imagination for these. And a useless animation. Very good. Okay. So just to give you some visual what happens to the electrons. I love these pictures because it shows you more clearly what happens. I'm going to move my person right here. So what happens if you touch a conductor, the charge doesn't stay in one spot. It actually will go as far away as possible. In fact, it literally goes on the outside of the object. Isn't that cool? So if I charge this, the charge is on the outside, not on the inside. So if I were to look at the electric field in here, it would be 0. I don't know why I'm talking into this. It's being silly. But the point is that the electrons spread out because they don't want to be near each other. So what happens is that if you were to charge this, the shock would be really teeny tiny because the charge distribution would be very small. And And also conductors, especially, touching other conductors will lose their charge really quickly. So when I do this demonstration in class, you'll notice I don't get as good as a spark as I do with my insulators. Now, insulators are really kind of cool because they just hold their charge longer because they don't move their charge. They stay in one spot. So if I took this, imagine, styrofoam cup, and I rubbed it at the bottom and put this next to an electroscope, you would see the electroscope get deflected at the bottom. But if I turned it around, it wouldn't get deflected here. It's pretty cool. That's because the charge, and I would do it again. I was like, charge, not charge, charge, not charge. We would find that that's because insulators keep their charge. And they have a higher charge density, so I'll get a bigger shock from this. Once again, I'm noting that this is not always the case. There are exceptions to all of these rules. So just know that is true. But again, I like to kind of simplify things here. Conductivity skills, not something I'm testing you on, but it just gives you an idea of the ability to conduct. So the best thing is silver. When I used to work at UConn, we used to do labs, and I remember I would have to make connections, and we had like silver nail polish. It looked like nail polish, but it was the best conductive material when we were doing, it was electrophoresis, I think we were doing. It was some complicated chemistry, physics thing I was doing. But anyway, I remember painting it with silver, and I asked like why silver, and of course it was the most conductive. Copper being the second. We almost would have had silver power lines if it wasn't so expensive. But copper is the next best thing, and as you can see, you can go down. There's these things called semiconductors, which sort of conduct but sort of insulate, and actually that's the it's really important just to mention because it's responsible for electronics. Again, this is a whole nother course. I took like 3 courses on electronics and covalent bond and all this stuff, like chemistry, but with physics involved about why things are conductive. It's pretty complicated. And that complicated nature is really helpful for our computers. And then, of course, the copper wires are good for connecting those two things, 2 wires. And then, of course, it's good to use, they don't put the word plastic here, but plastics to isolate, the charges as they go through a circuit. So, I might have heard of this, you're safe inside of a lightning storm. So just in general, again, I'm not an expert in this, so don't take my word. I'm just telling you the science behind it. But honestly, if there is a lightning storm, you should go in your house. But given the chance, given the scenario that you're by yourself and you have nowhere else to go, the next best thing is your car. Now, all of you might have heard that, you're safe because the tires are grounded, right? They ground you, or they're insulators, right? Well, that's partially correct. Actually, what happens is you're safe inside your car, not because of the tires, but because the fact that it's metal. Now, like I told you earlier about conductors will allow the electrons to travel on the outside of the object, which is pretty amazing. So if the car does get struck by lightning, a couple things. Number 1, your car has metal around it, so it's going to go around the metal. Number 2, the rubber tires doesn't block the lightning from going to the ground. I mean, if it goes from the sky to the car, it's going to have no problem going from the car to the ground. The rubber tires do not protect you. All it means is that the rubber tires don't get any of the lightning charge, which then again doesn't help you to begin with. So that's also true of this thing called Faraday cage. So if you've ever gone to the Boston Museum of Science, it's a pretty cool, it's worth it. Like if you had to do anything at the Boston Museum of Science, it's very kidsy, but this one's worth it, worth the wait. Go see it. And what they do is they put a person in a cage and they literally electrocute the person, well, not the person, but they electrocute the cage. And it turns out that the electricity, despite the fact that a person's inside it, goes around the outside of the cage, allowing them to be safe. And even to this really crazy extent is you can touch the inside of the cage because the electricity will travel on the outside. So you can see that demonstration here. Please do not try these at home. Do not test any of these out. You have to be, these are trained experts. I wouldn't I would probably do it, but I wouldn't advise you to do it. But anyway, all this fun stuff. There's a music group called Arc Attack. If you need some time suck, if you want to dive into something interesting, but there's a musical group dedicated to electrocuting themselves. They made a chain mail, so all metal bodysuits, and they electrocute themselves to music. It's a great class demo I like to show, but because I'm videoing, I'm not going to show it now. But Google Arc Attack. Write it down on a piece of paper so you can find it later. It's totally worth looking into. It's pretty fun. So just really quick. So you're safe because of the metal, not because of your rubber tires. People get this wrong a lot, and people rely on the rubber of the tires. Don't. Okay. Another concept check. True or false? Only conductors can be charged. Insulators cannot. Conductors tend to have more electrons than insulators. The plastic around the wire is used to insulate the wire, and the wire is used to conduct electricity. True or false? So why don't you take a minute to think about these, write down some answers to commit to. Normally I would have you do this in class. So I'm going to give you 3 seconds to think about some of your answers. So I'm going to go ahead and do that. Okay, number 1. False, insulators can be charged. Both conductors and insulators can be charged. 2 is false. It's not about the number of electrons, it's about the movement of electrons. And number 3 is true. That's based on definition. So insulator charging, it just left. Insulator charging is predominantly charged by friction. So basically taking 2 objects and rubbing them together. Now, since electrons don't want to move, the only way we could charge something is physically take them off by rubbing them. Now, when it comes to what materials used to do this, it depends on this thing called the Electron Affinity. So you don't need to study this, but just to show you that, for example, some objects are more likely to receive electrons and some are more likely to lose electrons. So for example, if I took some animal fur, which is the best kind when it comes to charging, again, I don't have anything that resembles any of these things, but if this is a rod right here and I charged it up with some animal fur, my hand, my animal fur would be positive and this would be negative. That would be like one thing. It's my lipstick. Fun. Keep it by my video camera now. But anyway, the point is that, one will be more positive because it likes to keep likes to get rid of its electrons, and like other things like plastic. So all this stuff down here, the polyvinyl, chloropolyethylene, polypropylene, these are all plastics. They're just chemical names for them. So plastics are usually negative, and fibers like wool and animal hair, silk are usually positive. And then you have some neutral things in here, like a rubber balloon is kind of relatively neutral. But once again, when it comes to charging insulators, it has to be done by rubbing. So plethora of examples. I did one already with the balloon and the sweater. This was like the old demonstration demo one that we used to have. But same thing. This is a rubber balloon and a wool sweater. You rub the two, and we saw that the electrons went on the balloon and the wool sweater was positive. But many other examples. So when your clothes are dried in the dryer, there's lots of friction in there. There's lots of rubbing, so that creates a lot of that charged objects. So most of, especially now when it's dry, if you take out your clothes, they'll be charged. Rubbing your shoes and carpet, animal fur and styrofoam cup, which is a typical classroom demonstration. And this is just a silly little cartoon of a girl scooting over and kissing somebody and getting electrocuted that way. Of the, 20 years of marriage I've had, it's only happened once in terms of like I walked to my husband and we gave each other a kiss and we got shocked. So this is not a very common thing, but I certainly do remember. It was really shocking. It was literally shocking, both in like surprise and shock. But anyway, so something that's really important too is that property of charge is that it's conserved during frictional rubbing. In other words, If exactly 10 electrons are removed from the rod, then there's actually 10 electrons that are gained from the rod. So there's no loss of charge, there's no generation of charge, which also means that if I take an object and I try to charge it, let's take my lipstick, right? And I take a cloth and I rub it, I can only rub it so much before all the charges come off. I can't rub this forever and then expect more and more and more charge to come from this. It's not infinite. So in other words, if you're going to go ahead and scuff your feet on the floor and try to shock your little brother or sister or your mom or dad or whoever, doing it all day doesn't change things. You could just do it for like a couple seconds and that's probably sufficient to do that. So you don't make charge, you transfer charge, just like energy. And same thing, when you remove the charge from one object, it doesn't go into the abyss, it goes somewhere else. Generally what happens is if you charge an object, say I charge this, I leave it here all day, yes, it's no longer charged because the charge will go into the air and the air will separate that charge and get rid of it. So that's usually what happens. But those charges that were lost on this can do in fact go somewhere else. Oops. Okay, I don't know why my titles are leaving, but they are. So now I'm going to talk about conducting. So I can charge conductors by two methods, by conduction and induction. Now I actually have to charge them differently than frictional rubbing. Frictional rubbing works because electrons are it's kind of like, I think of it like I'm in a meadow and I'm picking out the flowers. Like they're stuck there, so if I go pick up the flowers, they stay there. But if I were to, if I were rub it, if I tried to rub a metal object, it's like trying to catch bees. The charges don't stay in one spot like flowers do, right? Bees will go all over the place, so it would be hard for me to catch them. I know this is a silly analogy. But anyway, the point is that the motion of the electrons make it hard to rub. I could rub this, I won't really be able to charge it. But what I could do is I could do two other things. Just because I thought of it really quickly. I'm going to go back to insulators sorry, I took a huge sidetrack here. Only because I have some helpful knowledge, by the way. Fun fact. Fun fact about insulators and conductors. So, especially since we're all home now. I don't know if you ever noticed this, but if you have a glass bowl in your kitchen, right, and you want to put it away for later, you could put some saran wrap on it, right? So saran wrap will be this bright green. And the saran wrap, which is plastic, and the glass seem to get along. In other words, if you put plastic on glass, it kind of stays there and almost sticks a little bit, right? Both of these are insulators, so they work good in this combination. Ever try to do this? You ever try to take a conductor and put some plastic wrap on it? And if you haven't, you should try it, because actually you'll find that it's nearly impossible. Metal bowl. I mean, well, I won't say it's impossible. You can put the plastic on the bowl and it will stay there, but it doesn't stick like it does to here. That's because in order for an electron attraction, we need the plastic, we need the fact that these two are insulators versus conductors. So the best way for something to kind of stick to a metal bowl, you won't get that plastic that will stick really well, is to cheat and not use the sticking method, but use aluminum foil instead on a metal bowl. More that the fact that the aluminum is more malleable and you can kind of pinch the sides. It has nothing to do with getting it to stick like the plastic in the glass. So I noticed that a huge difference when it came down to using saran wrap. So I just wanted to give you some helpful everyday advice for that. But now I come back to the. Here we go. Okay, the two methods. Okay, so one's by touching, one is not by touching. So conduction is just a big word for contact. So you have to take a charged object and touch it to another neutral object. This one involves inducing charge. So in other words, we're not going to actually touch it. We're actually going to hold the charge away from this. Now you might say, well, why don't we always just touch the object? Why don't we just do that instead of this? Well, this is actually why lightning works. So what happens is, instead of someone taking a charge and holding it near, this is actually a cloud. And all the turbulence in the cloud removes charge. And what happens is that if this accumulates enough charge, it polarizes the ground. So the ground will become slightly negative, or something that's close by, right? So the closer you are, the stronger the electric field. So naturally, if I were lightning, I would strike the closest thing because I have the strongest force, right? So lightning would work like this. Lightning should be blue. Come on now. Would be like that. So that's where induction happens. Or if you build up charge without knowing it, you can get something to polarize. Like you can be polarized. Anything could be polarized. So it's a really interesting phenomenon. All right, let's see. So good news about, I don't know why my titles have left, I'm sorry. So this is conduction, charging by conduction, and it's really simple. There's 3 basic steps, and I don't even think I needed to say them, but you take so the important thing is you got to get a charged object. So this has to be charged already. Now notice the diagram has this little insulating feature so that the charge doesn't go into the person's hand. So that's important. So they charge this object. They physically make contact, okay? Now, note, in a real world setting, you can have this case where you have the charged object, and before you touch it, you hear zap. It's called zap with an S, zap. So, if you hear that, that's actually that little spark that you hear, that's actually a transfer of electrons. So you try to avoid this case. You want to actually physically touch the object so the electrons can travel through. I mean, this is okay, but you do want to actually have a physical touch and then the transfer of electrons. And then here's an example, right? Here's an electroscope. You touch the electroscope. Now the electrons want to leave here because there's too many. They want to spread out, so they'll go here. And then this now has charge because it received the extra charge from here. And that's pretty much it. So it's pretty easy. And it doesn't have to be negative. It can be positive. And if it's positive, and you touch something, so I just made a metal rod here, the electron flow goes the other way because those positives want electrons. So if you take a positive object and touch it to a neutral object, it will now become positive here because you lost electrons. Okay, pretty simple. I hope it's simple enough. Okay. I'm sorry. Should be not conduction, conductor charging. Sorry, my fault. I feel like this is going to be in several places, so let me fix this. Sometimes I type things and they look right. Alright, so this one's a little more involved. So induction's a little different. And in fact, there's 2 ways. I hate that they're leaving. There's 2 ways to do charging by induction. So the first way, let's move this right here, starts very similar. You're going to get a charged object, but now you're going to hold it near, but not touching. That's the important part. If you touch it, it becomes conduction or contact-based. So what happens is if you put it near but not touching, here this is diagram B, you cause the neutral object to start to polarize. You cause a shift in those electrons. And it depends on the type of charge that you see this shift. So in this case, it's all on the left side right here. So with a single sphere, what you're going to do is you're going to cause the charges to separate. And then what you're going to do is you're going to grab an object to, the word is called grounding. We're grounding by removing excess charge. But for now, we're going to take an object that is conductive. So your hand is pretty conductive. You can do this. Or you could take a metal pole, which is redundant because your hand is already conductive. But what if you notice the hand comes in and the electrons don't want to be near each other. They want to go somewhere where they can spread out. So they go into your hand. So they can spread out all over your body and then into the earth and on the earth. Holding it near but not touching, you still do this. And then what happens is you're left over with a charged object. It's going to be the opposite than what you had. So this is a class demo I would do. I'd put this, I put a soda can on a styrofoam. I would hold a balloon nearby, and then I would touch the side and you would hear it snap. It's a pretty cool little demo. And then, because this is charged, you'd hear a second snap. So you have to use your imagination. This is just a bigger diagram of this because I think it's just really helpful. And then this is an animation of that exact same thing that I just talked about. So you can see the charge movement and what happens here. So let's let it play for a second. And there you go. So this will repeat itself, so you can watch this a couple times if you need to see what happens. But I like the first part of this because it shows the polarization as you bring that nearby. So you can use a different method with two sphere separation. So instead of using one sphere, as you can see, I have a bigger slide in the other page. I guess I'll talk about that because it's better. I have it in words on the other page. What you do is you take two objects and put them next to each other. So this would be like two soda cans. I would take two soda cans and put them together. I would take the same object and I do the same steps. I take the charged object and allow for polarization to happen. And then once I allow the polarization to happen, instead of grounding it, I would hold that charged object here and then separate part B. When I separate the second one, notice that the charges are separated. So one side will be positive and one side will be negative like this. So then you have two of them. So in class I would do this and you would find that if I touched each of them, they would actually be charged too. So two-sphere induction uses separation of charges. Sorry. And single sphere induction uses grounding. So those are the big differences between the two. And same thing, I have this animation for you to show how the charges move in this case. There you go. And again, they show the electron movement and all that fun stuff. So you can see this work out. How to remove excess charge. So now that we learned how to charge objects, how does removal happen? Anytime we remove charge or neutralize an object, we call it grounding. The word grounding comes from the fact that charges like to go to the ground or the earth because it's the best place so that they can spread out and go forever. So again, like charges don't want to be near each other, and the best place for them to spread out and not be near each other is in fact the ground. It's the biggest thing, the earth itself. So that's where the grounding comes from. But in order to ground, you have to use a conductor to do that. So you need to allow the charges to move. If I became charged and touched a styrofoam cup, I would not release those charges because they won't be able to move. And that's the whole point of insulation. Even your utility poles are insulated. They're insulated with ceramic and glass so that the electrons don't travel down the utility pole into the ground. So that's the whole point of it. And I say people are good conductors because that happens all the time. Like when you touch a doorknob, you can scuff your feet on the ground like John Travoltage here. So let's show you John Travoltage. Here he is. John Travoltage. There we go. Charging by friction. And then he does gazam. He's touching that doorknob. Now I'm going to do this and notice that without touching the doorknob, that nothing happens. And also another important fact is in order for charges to jump, you have to have enough electric field nearby, and that only happens when you are at close distances. So notice I had to be pretty close for that to happen. So just like lightning strikes, you know, they always say be the smallest thing on the ground. Well, that's true because the further apart you are, the less the electric field is. And we can literally calculate this, which is pretty cool. I've actually gotten shocked by the water fountain. So annoying. I actually had Quinnipiac too. I remember I was like, man, because water is a good conductor, and I'm a good conductor, and for whatever reason, the water, as it's coming out of the fountain, can actually create some friction, therefore it can be shocking. So fun fact about Quinnipiac. But these are all ways you can ground yourself, touching anything, pretty much metal. So a couple other things about grounding. Anytime you neutralize an object, that's considered grounding. So actually during the induction process of the single sphere, you actually were grounding. You're getting rid of excess charge or allowing the charges to spread out. So some myths, rubber tires are grounding. They're insulators, so to use the word grounding is not correct. They do connect to the ground, but in fact, electricity wouldn't be able to travel through them because they are insulators. Another myth about grounding is that you need to connect to an object that goes to the ground. You don't need that necessarily. Some people, will ground to pipes, which is okay in certain situations, and you might need to do that. I'm not saying it's wrong, but I'm just saying that you don't actually need to physically touch the ground to ground. Grounding means removal of charges, so just know that. And then lastly, let's do our concept check. So let's see, a positively charged pop can is touched by a person standing on the ground. The pop can subsequently becomes neutral. The pop can becomes neutral because of which of the following? So electrons pass from the pop can to the person, or the electrons pass from the person to the pop can. Electrons pass from the pop can to the person. Protons are protons. So when you think about stuff like this, I always draw pictures because I just think it's better. You have a positive pop can, and a person touches it, right? So here's a finger, and they're touching it. So we want to neutralize this. We want to ground this. We want electrons to be added to the pop can. So electrons pass from the person to the pop can B. And that's another way of talking about neutralization or grounding. So there's negative and positive grounding. This is true. If you touch a negative object, they'll go down your arm because you're getting rid of that charge. So you can see the charge transfer in this case is leaving the object. If the charge transfer is leaving the object, then the object was originally negative. So that's what it means by negative charge grounding. And then positive, you add electrons to kind of neutralize it. So if you touch a positive object, then electrons go to the object that it's neutralizing. So think of it in terms of neutralization instead of positive and negative grounding, although I like that it shows you what happens to the transfer of electrons. That is something I do like, but I don't really go crazy about positive or negative grounding. But that's it for this lecture slide. So a lot of conceptual information here. So when it comes to charge interactions, the biggest thing is that you can have a, what happened to my video? I'll just put this on here. There we go. I'll just leave this here. So with interaction of charges, the biggest thing is that you can actually attract neutral objects if they're polarized. Polarized means that objects are still neutral, but you separate the charges to make it appear that it's charged. Insulators and conductors change the way you ground something because of their electron movement. So you can charge objects through friction, or you can charge insulators through friction, and conductors through conduction, which is contact, and induction, which is no contact. And anytime you neutralize something, you're grounding that object. And that is the basis right now, all electrostatics and electrocharges like that. Okay, if you have any more questions or need to talk about it some more, just let me know. Bye, everybody.